Hi there, Mike Holler and PG Mike coming back at you with Combustion Efficiency Secrets, second installment, the physics. Now last week we covered the chemistry, and by looking at what actually happens as we oxidize the fuel, we now have a better understanding of this whole conversion process from chemical energy to thermal energy. Well, this week we're going to take that thermal energy and we're going to do another conversion. We're going to convert that heat into useful work at the flywheel. Now, chemical energy doesn't do us any good. We got gasoline in the tank. It's not powering the vehicle as gasoline. So we burn the fuel. Now we got heat. We covered that last week, right? Now, the heat itself doesn't do anything. Don't believe me? Take a blowtorch to an engine. Does it start cranking? No. So we need to do another conversion where we're going to convert the heat energy that we now have by burning the fuel into what we call kinetic energy, useful work done. Now this whole process of converting chemical to thermal, we need a mechanism, something that we can take the heat and apply it to that can give us something useful. The nitrogen in the air. Well, the air that we're drawing into the engine is 78% nitrogen, right? We got about 20.8% oxygen. The oxygen is chemically consumed in the whole oxidizing process. So, we still have that 78% nitrogen. Now, as the fuel is burned, it starts converting the hydrocarbon element of the fuel with the oxygen into water vapor and carbon dioxide. You with me so far? Good. Now, when we heat nitrogen, it expands. I think it was 4th grade where my teacher took a glass bottle, milk bottle. Yeah, I'm old enough to remember glass milk bottles. And put a balloon over top of that bottle and put that bottle on a Bunsen burner and then lit the Bunsen burner. Now we've got heat on the bottom of this bottle. The air inside this bottle is now starting to get hotter, and as that air starts to heat, it starts to expand. The molecules start bouncing further and further and further apart. You with me? And then as that happens, the balloon just went from flat to a little bulge, and then a little globe, and then a bigger globe, and a ball, and then a beach ball, and then poof, it popped. Well, just before that ball popped, it was like 60 times the size of that original bottle. It had expanded that much. In an engine, as we burn the fuel, we generate heat. That heat acts upon the nitrogen in the air and expands it out. And if it has nowhere to go, it creates pressure. Well, the weakest link in the chain in the engine is going to be the piston. It's going to give, right? So we create pressure inside the combustion chamber. That pressure acts upon the surface of the piston, starts pushing it down. Now, as we burn the fuel, we're also creating water vapor. Remember, the hydrogen from the hydrocarbon combines with the oxygen, forms water vapor. Well, water vapor expands at 12 times the rate of nitrogen. That means that if you took a given volume of nitrogen at laboratory temperature and a given volume of water vapor at laboratory temperature, and you applied the same amount of heat energy to both, and you watched the balloons or you watched the pressure gauge, you would find that the water vapor creates 12 times as much pressure as the nitrogen does. The carbon dioxide that we get from the burning of the carbon element of hydrocarbon, oxidizing it, combining with oxygen, getting carbon dioxide, well, the carbon dioxide expands even more than the water vapor. What we have now is what scientists and engineers call an expansion medium. That is the mechanism where we take and convert the thermal energy in the fuel to pressure, which pushes down on the piston to turn a crankshaft to do useful work, kinetic energy. Now, you with me? Great, let's move on. When we burn the fuel, create pressure, this whole thing takes time. So getting back to the burning of the fuel. If you remember last week, we talked about, hexane, dodecaine, and everything in between octane. Hexane will take less than a millisecond to fully oxidize. Once you start this oxidation process, in other words, once you light it on fire, in less than a millisecond, you will get water vapor and carbon dioxide from that hexane molecule. Less than a millisecond. Dodecaine, the heavy element in gasoline, takes over 33 milliseconds. Why is that significant? Well, first of all, liquid fuel doesn't burn. Only the fuel that is fully vaporized, homogenized with the air can actually burn and produce heat. So let's assume that we have a fully vaporized dodecaine molecule, which is a highly improbability because dodecaine vaporizes at 435 degrees Fahrenheit. Hexane vaporizes at 135. So we're going to get a lot of hexane vapors when that spark plug goes off. We're not going to have very many dodecaine vapors. But still in all, let's put this into a perspective. Now, an engine at 2,000 RPMs, 2,000 revolutions per minute. If we want to know what the revolutions per second is, we can just divide it by 60. That comes out to 33.333, repeating, 33 and a third revolutions per second. Now let's put a time number on that. So we take 1 over 33.33, repeating. You with me? That gives us 30 milliseconds for one complete engine cycle. 30 milliseconds. Now, since we're only dealing with top dead center to bottom dead center, because we're talking about the power stroke, so it's like half of a revolution. Now we take 30 divided by 2, now we have 15 milliseconds. That means that from top dead center to bottom dead center, that whole process will occur in a mere 15 milliseconds. Now let's consider the spark plug goes off a little before top dead center, and let's also consider that the exhaust valve opens before bottom dead center. Just to keep the math and the illustration easy, let's still say 15 milliseconds. So from the time the spark plug goes off, sometime before top dead center, and the time that the exhaust valve opens, sometime before bottom dead center, let's say it's 15 milliseconds at 2,000 RPMs. Well, if we have hexane that takes less than a millisecond to fully oxidize once the burning process begins, we're good to go on that. But the dodecaine, even if we were able to vaporize it, and even if that dodecaine happened to be between those spark plug electrodes when that coil went off, and even if we ignited that dodecaine at the earliest possible point in the whole process with the spark plug ignition point, it still is only half, but less than half burned when that exhaust valve opens and starts bleeding off the pressure. Goodness gracious, can you see how there's a little bit of a problem here? Can you see how gasoline is not a very compatible fuel for the gasoline engine? Well, US EPA says the gasoline engine is 18.2% efficient when running on gasoline. 18.2% of the chemical energy in that fuel is actually converted to power at the crankshaft. Now there's additional losses, tire, rolling resistance, accessories, but you got your biggest losses in the internal combustion engine. If you take that same internal combustion engine and run it on propane, now EPA says you're at 42% efficiency. We just more than doubled the efficiency just by going from a liquid gasoline to a vaporous, much smaller 3-carbon hydrocarbon fuel, propane. Now if we take that same exact engine that was 18.2% efficient on gasoline, 42% efficient on propane, and we burn natural gas in that engine, now we are 60% efficient. Why? Because that single carbon hydrocarbon natural gas fuel molecule burns so quickly and so cleanly in such a short period of time that we're able to extract 60% of the available chemical energy in that fuel and convert it to do useful work at the wheels. I guess gasoline's not a very good fuel for the gasoline engine after all, is it? So here's the deal. anything we can do to speed up the burn. And we're going to go into this a lot more in the third and final segment of this combustion efficiency series. But anything we can do to speed up the burn is going to provide more power, lower emissions, and ultimately improved fuel economy off the exact same fuel we're feeding the engine. Now that's kind of a lot to think about. We covered the gasoline combustion chemistry last week. This week we put it into terms of physics, and next week we're going to tie it all together. I'm going to show you what that really means in a real world fuel economy project. Thanks for tuning in. MPG Mike, I'm on your side.